This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 2 weeks. Thanks to our audience and the partners listed on our website for supporting the podcast. So, welcome listeners to this new episode of Software Engineering Radio. This is once again a language episode, and as I think mentioned a number of times before, these are some of my, the episodes I probably like most. So this time we're going to talk about Clojure, and our guest is, Mr. Clojure, Rich Hickey. Hi.
Hi.
Thanks for being on the show. Why don't you introduce yourself before we're talking about your creation?
I'm Rich Hickey, and I wrote Clojure. Clojure is a dynamic programming language for the JVM. It also runs on the CLR. Has sort of 4 primary characteristics. It's a Lisp. Mm-hmm. It's designed to be hosted, so it has an intimate relationship with the host platform. For instance, the JVM. It's mostly functional, so it has an emphasis on immutability and pure functions and immutable data structures. And it has another focus on concurrency. Mm-hmm. So all the aspects of the language were designed to have meaningful semantics in the context of a concurrent program.
Okay, and we're going to explore that later. I just wanted to make our listeners aware that we've had an episode on Lisp before. I just checked. It was episode 84 with Dick Gabriel. So while we're probably going to talk about Lisp basics shortly or briefly here, we're not going to do a full introduction to Lisp. We probably won't have the time. So if you're not familiar with Lisp at least, generally, then you should go back to episode 84. So I guess, nonetheless, Rich, it would be a good idea if you introduced Lisp. Basically, what are the fundamentals of Lisp? How is Lisp different from other languages? And maybe why is it special, as many people would probably say?
Okay, well, the last question is probably the best one, because many of the things that Lisp innovated have become widely available in programming languages. I think the thing that still makes Lisp unique is that programs are presented to the compiler in the forms of data structures. Mm-hmm. So a Lisp compiler does not compile text; it compiles data structures. And when you do write a program in a Lisp like Clojure, you write it in terms of writing literal data structures. So if you do place text in a file, what you do is you place text that contains data literals.
But how is this different from a programming language that parses some kind of text and builds an AST, which is also a data structure, and then feeds it into the compiler?
It has a lot to do with whether or not that AST is made up of the kinds of things your program normally manipulates. So in a Lisp program, and particularly in Clojure, the data literals are the things that you use every day: vectors and maps. Mm-hmm. And lists. And so there's a huge library of things for working with them. It's not a special library for working with an AST tree. It's the regular data processing library of the language, which means that you don't need to write special or unusual code to manipulate the AST. You write ordinary data processing code.
So you could say that programming and metaprogramming is the same thing.
Exactly. They're no different. And that really matters. I mean, if you've ever worked with an AST library that presents an object-oriented approach to an AST, you realize you're writing to a very particular API. And when you write macros in Clojure or a Lisp, you're writing very ordinary data structure processing code.
Mm-hmm. So. What are the data structures that are used? You already mentioned, I think, vectors and lists, right? So a Lisp program is basically a set of nested lists. Is that right?
That was true for Lisps traditionally. For Clojure, there are several other data structures that have the same first-class status as lists do.
Okay.
That would be vectors and maps, which are like hash tables.
Right.
And so there are forms in the syntax of the language, which is again defined in terms of these data structures that utilize vectors in particular, and sometimes maps.
Mm-hmm. So you alluded to it, and I guess it's also obvious from episode 84. Lisp isn't new. Lisp is a quite old approach, and it has been used successfully in some domains, but it has never really, gotten mainstream. So I guess, do you have an opinion why it never got mainstream? And then, of course, the related question is, why did you, implement your own Lisp in 2000 and, I don't know, 8, 9, or 10?
Well, those are two separate questions. So why did Lisp never catch on as a mainstream language? I'm not sure it was designed to be a mainstream language.
Okay.
I think at the time it came up, it was really designed around super users, researchers, and very smart people who are trying to solve very hard problems.
Yeah.
And Lisp sort of maximally leveraged their efforts. You could sit in a Lisp environment, and as an individual person, you had an incredible amount of power. I think we all know that programming in the large is more of a social activity now that involves other people. It involves libraries. It's particularly critical to be able to interoperate with things other people have done, either in the same or in different languages.
Mm-hmm.
And so that's an area where Lisp didn't do as well traditionally, because these boxes and the approach were, they were like islands. They were very nice islands with great, pretty trees and beautiful views.
Yeah.
But not well connected, I would say, to the rest of the world.
Mm-hmm.
There are some other, social and historic reasons that have to do with artificial intelligence and its demise in the 80s and 90s, which, and being tied to that, meant Lisp sort of lost favor when AI did.
Mm-hmm.
But it never lost its power. So to get to your second question, why would I do this today? The second half of the feature I wanted to describe as still being unique to Lisp is because the programs are represented in data structures. It means you can write programs that write programs.
Mm-hmm.
And the second key aspect of a Lisp is that when the compiler is evaluating your program, it gives your macros, which are also small programs, the opportunity to run during the compilation process, which means that your program writing programs can be integrated with the compiler.
Yeah, I think that's a very important aspect, because it's really not a big problem to write a program that uses, let's say, the Eclipse AST API to create a Java program. It might not be as simple as lists, but, well, I guess that's a matter of taste. But the ability to plug it into the transformation or compilation process, and make it kind of seamless by that's important.
Right. So that enables a feature called syntactic extensibility, and that's a powerful thing. It's important for programs in the same way that function abstraction is important. We don't want to keep writing the same things over and over again.
Right.
We want to write them once and reuse them. And so there are many patterns in software that can't be well encapsulated by objects and methods. The simplest example would be in a Java program, the try block and the kinds of frequently occurring patterns that you have to write over and over because you have no tools for encapsulating them in something that eliminates the repetition.
Yeah.
So
yeah, go ahead.
Yeah, so that I consider that to be an extremely valuable thing and worth pursuing still. So what I wanted to do was make a Lisp that retained what was powerful about Lisp, but addressed the island problem.
Mm-hmm. Yeah.
So Clojure, in being hosted and being on a host, not being an implementation detail, merely the fact, but something that's a feature. And exposed is really important, and because that means that now, as a new language, for instance, Clojure has full access to all of the Java libraries.
Mm-hmm.
It has a great ability to interact with Java programs, and you're immediately off the island.
Yeah. Yeah. Well, I'll get back to that later. I just want to return again to briefly to this meta programming stuff.
Sure.
You said that syntactic extensibility is an important concern and measure of the power of a language like Lisp. Now, if I would play devil's advocate, I would say Lisp has no syntax. I mean, if you represent everything as lists, then it's of course simple to represent everything as lists. So, and of course I'm exaggerating a little bit, but what I'm trying to get at is it the fact that Lisp is so extensible regarding its syntax, the growing a language thing that Guy Steele had a while ago, is that because the syntax is so kind of trivial and almost non-existent? I mean, it's not so easy to be able to do that with Java, for example, independent of the meta-programming facilities. So how important is the syntactic simplicity to be able to do what you described?
The argument is that it's pretty important. There aren't many meta-programming systems as easy to use as Lisps.
Mm-hmm.
I don't think it's about lists. Everything is a list. In fact, everything is not a list in Clojure.
I know you said it before. I'm exaggerating a little bit. Yeah.
And I think it's important because there's a sense in which when everything is a list, it's actually a little bit more complex, right? Because that means lists are more overloaded. Mm-hmm. Because there is a syntax. It's not actually in the character representation very much, right? The characters are just used to represent the data structures. Yeah. But then there's a syntax in terms of, what is the interpretation of the data structures? Mm-hmm. And that's where the syntax lies.
More on token level instead of on character level, if you will.
Well, yeah, tokens and even bigger, lists and nested vectors and things like that.
Right.
So that's where the syntax lies. I think the fact that that the syntax is data structures, and when you write a transformer, you produce new data structures. Again, these very simple built-in common data structures does make the metaprogramming much, much simpler.
Yeah, I agree. Yeah. So you mentioned that the target audience of classic Lisps back then being the scientists who does AI stuff. Who is the target audience of Clojure? Is it really like Joe Java developer, or is it also do you think they would like a Lisp-like language? I mean, who did you target it at?
I think any programmer with a sufficiently open mind will find working with a Lisp a thrilling and tremendously fun experience. Mm-hmm. That was my experience. I had more than a dozen years of C++ and Java and C# and Lisp is just tremendously enabling. Mm-hmm. And I think that many people's initial reservations about Lisp are very superficial.
I agree. Yeah.
Because at the core, for instance, Clojure is much, much, much simpler than Java. So once you can see that, you say, "Wow, it's simpler and potentially at least more succinct, but potentially more powerful."
I guess I think the discussion that people have around this is probably maybe that there are two different notions of simplicity. I mean, you could say that Lisp is simple because it has a very simple syntax only consisting of the couple of abstractions you mentioned before, and then it's very orthogonal. You can kind of, write code that writes code that writes code and stuff. But the other person would say Java is simpler because I'm guided more. I have more specific language construct, so I'm not so out in the cold. I'm much more guided along a predefined path, and that can also be interpreted as some kind of simplicity. So I don't know what I'm going to say. What I wanted to say.
Well, I think that most of that people's simplicity there is a matter of familiarity.
Yeah,
I think when you take somebody off the street and you show them Hello World in Java,
yes.
If you really tried to explain every line of that program,
yes,
you would realize how complex Java is. We've just become comfortable with that, but it's not simple at all.
I agree. And
when I'm talking about the simplicity of a Lisp and Clojure in particular, I'm not talking about syntactic simplicity, although that's there.
Yeah.
I'm talking about the lack of implicit complexity.
Yeah.
which is really where we suffer.
Right. Yeah, I agree. I have to say I don't have any practical experience with Lisps, but I can see what you're saying, and I would actually like to do some, spend 4 weeks and do something meaningful with Lisp to get some experience. 2 weeks ago, we had a little open space conferences about DSLs, and we got together 10 people, talked about different tools and languages and facilities to build domain-specific languages. And one person showed a couple of Lisp examples, Martin Fowler's state machine example in Lisp, and it is very elegant. So I can really imagine, or I can understand what you're saying. I just can't appreciate it from my own experience. That's why I might sound a little bit skeptical, but it's really just I don't mean it that way.
Yeah, I think I absolutely acknowledge the familiarity aspect is important and is an impediment.
Yeah.
That people need to get past if they're going to discover what's possible.
Yeah.
But it is more a matter of familiarity than it is simplicity.
Yeah, it's funny. I have the same. I use the same arguments when I try to convince people of, let's say, using MPS projectional editor to write code instead of a normal ASCII editor. And I also say you have to believe that at the other end, the grass is much, much greener, and you have to go through this pain. So I guess it's, yeah.
Yeah.
So what's different from normal Lisps or classical Lisps? You already mentioned the fact that it's very well integrated and explicitly integrated with the VM, and I guess we'll talk about that in a minute. But from a language perspective, what's different from Lisps?
Two things are the primary differences. One is in traditional Lisps, the core data structures are mutable.
Okay.
So they have, con cells to represent lists, and people should be aware that, like Common Lisp has vectors and it has arrays and it has hash tables and all the modern data structures, but they're all mutable. Mm-hmm. So that's an area where, for instance, because I wanted the primary data structures to be immutable, I couldn't retrofit Clojure on top of, say, Scheme or Common Lisp.
Right.
The second area in which Clojure differs is that Lisp is very old, and
yes.
and Scheme is very old, and they actually predate some modern concepts like interfaces and polymorphic API design.
Yeah.
Because they came from before. Lisp innovated in areas as simple as having conditionals.
Yes.
So Clojure has an API design that's built upon abstractions. So where in a traditional Lisp, there's a library of functions for dealing with lists, they really were hardwired to a particular data structure. Similarly, there were functions for dealing with vectors and with maps, and they work specifically with the concrete data structure supplied with the language. Mm-hmm. In Clojure, there are abstractions behind all of the data structures, and all of the library code is written in terms of these abstractions. So you can imagine them to be Java interfaces.
Right.
And they are, in fact, Java interfaces under the hood. Mm-hmm. That means that the entire sequence library works with anything that's remotely sequential or could provide a sequential view. Mm-hmm. And that's a big deal because now you get far greater leverage out of library code than you would otherwise. So those are the two biggest differences, that the core data structures are immutable and the built-in library is built in terms of abstractions and not concrete data structures.
Mm-hmm. And I guess so. I mean, Common Lisp had object orientation, although in a somewhat different way than we typically know it from mainstream languages today. Do you have that too? Can you define classes in Clojure, and how are they different from Java classes, or maybe they aren't? So how do you go about that?
There are sort of two things that you can do. One is you can define classes and interfaces that are, in fact, Java classes and interfaces. Mm-hmm. And that's there for interoperability. It's also there as an abstraction tool. In the coming versions of Clojure, there are these things I call protocols, which mm-hmm. they're kind of like Java interfaces, with the benefit being that you could extend an existing class for which you do not, over which you don't have control to participate in a protocol, mm-hmm. whereas an interface requires you derive.
Yeah.
And so that will be the main abstraction mechanism. That's still not an object-oriented oriented system for Clojure in the same respects as you traditionally think of objects. I mean, most people think of objects as mutable, stateful
Yes.
things. And so Clojure still won't provide that except via the Java interop facilities.
So the basic abstractions you're going to create in Clojure is basically data structures and functions that work on them.
Correct. But with protocols, you still have the ability to define sets of functions as abstractions with names and get polymorphic behavior.
Right. Okay.
So I like polymorphism, and I think it can be, pried out of object orientation and delivered a la carte.
So in that sense, those protocols would kind of act as an adapter then to other data structures that don't yet implement the behavior directly?
They are like adapters, except they do not require wrappers.
Ah, okay. So there's some compiler magic going on.
Yeah.
Okay. Which leads me to the question, which I kind of already answered. It's compiled, right? It's not interpreted.
Correct. There's no interpreter in Clojure.
So
you still get dynamic code loading, and you have a REPL. It's just that everything is compiled as it's loaded.
REPL means read eval print loop, right?
Right. Read eval print loop.
Eval,
so that's your interactive, interface.
Yeah. So have you done any performance measurements comparing Clojure with, say, Java?
Yeah. In terms of calling normal methods, Clojure is the same speed as Java. It emits the same bytecode.
Right. Okay.
The big performance difference with Java is that in Clojure, in normal Clojure code, numbers are always boxed.
Mm-hmm.
So you're always getting the big I integer, big L long. So that has performance overhead. And obviously math with that is slower. Arithmetic with that is slower.
Yeah.
However, inside a function, you can declare primitives, like int and long, exactly the same as Java, and the arithmetic with those can be made the same as Java's.
Right.
Of course, there are different levels. By default, a Lisp has automatic promotion of integers to as large a data type as is required to hold the result.
Yeah.
And Clojure offers three flavors of arithmetic. One that does that, one that does native primitive arithmetic, but with overflow checking, which is still safe.
Yep.
And the third kind is, essentially bad, which is what Java does.
Yeah.
I mean, Java has silent overflow. So
right. Yeah.
If you want that, that's the fastest possible thing, and it's available in Clojure.
Mm-hmm. Okay. So I guess we should talk a little bit about Clojure's approach to concurrency, because first of all, I guess concurrency is an interesting topic these days in general, and you said that was a motivation or was one of the important characteristics of Clojure. So I guess one aspect of being concurrency friendly is the thing you mentioned before, immutable data structures, right? Can you elaborate briefly on that?
Sure, I would definitely want to start there. I think in the broadest sense, Clojure's approach to data structures and object orientation and concurrency are all tied together, and they have to do with they're all born of a frustration of dealing with state.
Okay, I think I saw your talk about time, right? I think the QCon, or where was it?
Sure, that was at the JVM Language Summit.
JVM Language Summit. Okay, yeah.
Right. So yeah, I mean that's what Clojure is really about. Even if you don't have concurrency, I think that large object-oriented programs struggle with increasing complexity as you build this large object graph of mutable objects. In really, trying to understand and keep in your mind what will happen when you call a method, and what will the side effects be, and where will it have impact.
So, and that's just simply because things have side effects, or are you referring to something more I don't know, more strange?
No, I'm talking about mutable objects.
Right. Okay.
As simple a thing as if you're given a mutable object, can you maintain a reference to it?
Yeah.
As a value, Can you go back to it later and know that it will be the same value, represent the same value? Those concepts are merged together in object-oriented programming languages, and there's a sense in which that's broken.
I think what you called it in your presentation at the Languages Summit was the distinction between state and identity. Am I correct?
Correct.
Okay, yeah.
That's right.
So the identity remains the same over time, but the state and the value of something changes.
Correct. And if you're able to obtain those values, it means that you're able to make a huge portion of your program independent of the identities and the change part.
So in other words, you would store values and not identities.
That's right. You can remember values quite easily, and you can perform computations on them without worry.
Yeah.
And we should do that more. I think the fact that when we start in an object-oriented language and we make a class and we get mutable fields by default, we have far more mutation than we require.
Yeah.
And it takes an incredible amount of discipline to remove that.
Yeah.
So Clojure takes the opposite approach and says, let's start with programming with values, which don't change, and do as much as we can with that. And then, and only then, when we need, an identity, we'll deal with that independently, again, trying to make orthogonal decisions about things. So we start with how do we program with values, which goes to your first question, which is, how do you represent things that are bigger than, numbers and strings as values? You need efficient data structures for representing collections, for instance, as values, or even small ones that would have been objects. And so Clojure comes with a suite of data structures they're called persistent data structures. Persistence doesn't have anything to do with being stored on a disk. In this case, what persistence means is that a data structure is immutable. It means that if you were going to do something that would change it, what you're really going to do is produce a new version of it.
A copy, basically.
Excuse me?
A copy, basically. Copy on chains.
Well, no, because then the next feature of a persistent data structure is that the data structures have performance guarantees, the big O guarantees that you would expect.
Okay.
So if the big O guarantee of a data structure is that you can add something to it in log n time.
But let me try to say it differently. It feels semantically like a copy, but it's not a brute force duplication of the data structure, but there is rather some more clever stuff going on.
Exactly. That's the real key. But the thing is, it needs to be said because people's first intuition is that this will require copying.
Yes.
And that can't be made efficient. And that's not what's happening. So persistent data structures, you make a new version. The new version can be made while meeting the performance guarantee. So that already implies that it's not a copy. Right? Because if it promised log n and it had to copy, that would be linear time.
Yes.
The other attributes of a persistent data structure is that the old version is still available. It's not destroyed, nor is it degraded. So the performance of the old version is as good as it ever was. Because there are schemes for doing persistence that sort of have the old versions degrade over time. I don't know why. Because of the way the structural sharing might work.
Okay.
So the first class persistent data structure, the old versions are as good as the latest version.
Okay.
And when you have all of those things, you have a completely different tool in your hand for doing programming. Remembering values is easy. Storing undue stacks is cheap. Doing speculative work in a recursive fashion is inexpensive. And dealing with concurrency is easy because these values are immutable. They don't require any locking or anything else to be used in a concurrent context.
So I guess it's worth spending 5 more minutes on this persistent data structure thing because I kind of almost forget about it. And as you remember, it's not in the agenda, but it's a very important point. So assume I have, let's say, an expression, just to make it simple. I have an expression that multiplies 2 with the sum of 2 other numbers, like 2 times 3 plus 4, just so we have some kind of tree-like data structure.
Okay.
And now I replace the 4, the 2 times 3 plus 4, I replace the 4 with a 5. So trivially, I'd have to copy the whole data structure, and that's not what's going on. So can you briefly explain how this magic works so that you get a copy and don't copy?
Well, if we take the simplest persistent data structure would be a singly linked list.
Mm-hmm.
So if I had a singly linked list that was A, B, and C, and you wanted to prepend,
Yep.
X, you could make a new node,
Right.
X, and you could have its tail point to my list.
Right. In that case, it's trivial. Yes, I agree.
Right. So, but the important note there is that there's structural sharing.
Mm-hmm.
Right. Your list shares its tail with my entire list.
Mm-hmm. And because I can never change anything, that can never be a problem regarding, something changed over here.
Exactly. That's the other key thing is that because I can't change my list.
Yes. Right.
I can't harm your list.
Right. Mm-hmm.
So to scale this concept to any other data structure, you move from a list to a tree.
Yep.
And basically all of the Clojure data structures that would be, hash maps or vectors are represented as trees.
Mm-hmm.
So as soon as you've got it represented as a tree, it means that you only need to copy the path to the part of the tree that you're changing.
Right.
As opposed to the entire tree. For instance, if you represented a vector as an array,
yeah,
you would have no hope but to have to copy the entire array.
Right. I mean, in some sense, you can see a tree as a set, as a number of linked lists, in the sense that every node doesn't just have one tail, but many tails, and that gives you a tree.
You can, of course, the implementation doesn't work that way.
No, but mentally,
right, exactly. Well, that's why I started with the list, because it is essentially you have chains of things, right? And as soon as you have a tree structure, then modifying any leaf in the tree only requires copying the path to the root.
Right.
Mm-hmm. And nothing else. And the new tree shares everything with the old tree except that one path.
Mm-hmm.
So Clojure's data structures are trees of arrays. So they have a very high branching factor and they're very shallow.
Mm-hmm.
And that ends up being very fast.
Mm-hmm. Okay.
And that's how they work.
Good. So I guess that's the whole thing about immutability, which, again, if you don't share anything that is mutable, you don't have to lock. So you remove all the locking issues immediately.
Right.
But then, of course, people will say that if you never change anything, how sensible can a program be? So I guess at some point you need to be able to change some things. I mean, a database is something that changes. So how do you deal with, do you deal with data that changes? And if so, how?
Yes, well, that's really the key. That's the key thing about Clojure is that it makes no attempt, and it doesn't purport to say that you could write programs with only pure functions and immutable data.
Yep.
Because they, realistic programs that operate over extended periods of time and get input from the outside world and interact with the outside world do have state.
Yep.
So how do you do that? And the key thing is to realize the difference between the value and the notion of an identity, right?
Mm-hmm.
Which is something you might talk about over time. So the example I'll use here is imagine a program that has people log in and out over the course of it running.
Mm-hmm.
The set of logged in users is a collection.
Mm-hmm.
In a traditional program, you might consider that to be something that's mutable, the collection itself.
Right.
So when somebody logs in, you would actually, change that collection. And that ends up being a big problem because now you have the possibility that somebody was looking at the old version and iterating over it, and now they get a concurrent, a modification exception.
Yep.
So then you have all these difficulties. But what's really happening is that there's this identity, which is the thing you're naming, right? The set of logged in users is an idea.
Yep.
And at any particular point in time, it has a value. So if you represent those values as immutable collections, then all you really need to do is ensure sequential relationship between the idea of the set of logged in users and a particular set, a particular value.
Okay.
And that only requires a little atomic data structure, right, which is a reference to the value. And you can give, and that's the thing whose contents change.
So let me try to recap. Clojure provides something called an atom, right?
That's one of the possible things,
Yes.
right?
And an atom is a wrapper around a value, where, of course, the value in the wrapper can change over time. It provides an identity, and it ensures sequential access to the wrapped data.
Right. So I would take that one level higher. So atom is an example of one of Clojure's reference type. One of Clojure's reference types.
Mm-hmm.
And so the reference types are all about the same problem. They're about giving you a tool for representing identity and giving you a tool for managing time and the succession of states associated with an identity.
Okay, give us an example. How does that work?
So you can imagine these references to be a little box,
mm-hmm.
right? And in the box is a value. And by value, we mean something that can't change.
Right.
So the set of logged in users will be a box. Inside the box at any particular point in time will be an immutable set data structure.
Mm-hmm.
And when you want to add a user, you're going to take that immutable value, you're going to call a function on it, produce another immutable value, which is that set with one more user in it, and want to associate that new value with the identity, which is the set of logged in users.
Okay, but if two people do that at the same time from different threads, then you run into concurrency issues.
Except that these reference types have concurrency semantics.
Aha.
That's their job.
Okay.
So the trick is to separate the two problems. So we're no longer talking about the problem of actually modifying a collection to put another thing in it.
Yep.
That's it. Those are functions on values. What we really are left with is just a problem of saying, how do we go from one state to the next, where each state is a value?
Okay.
Without colliding with each other.
And how does this? Go ahead. Yeah.
Go ahead.
I was just going to say, how does this feel from an API perspective? I mean, what do I do? I mean, I have such an atom here, one of those reference data types.
Okay.
And what do I do?
So if you have really any of the reference types, they all have the same shape to the interaction. In other words, there's a single model for changing state.
Mm-hmm.
And that is given some reference in which there's a value you want to change. You're going to pass that reference a function, which is a function of the value that's in there.
Okay.
Possibly some additional arguments. The reference type itself is responsible for taking the function you've given it and applying it to the value and making the return value of that function the next state of that reference.
Right. And the reference type makes sure that only one of these functions is executed at any time.
Correct. So, of course, this implies that you have to have first-class functions in your language.
Sure, yeah.
Right, so you can pass a function
yep.
in. And then there are different semantics possible for how and when the change will occur.
Mm-hmm.
So the change could be synchronous or it could not be synchronous, right?
Mm-hmm.
You could ask for a function to be applied to the value and want to know when that call returns that it's happened.
Yep.
Or you'd be happy to say, please do this eventually and go on.
Mm-hmm.
That would be the asynchronous case.
Yep.
So there are differences there. There are differences with whether or not the change you want to make impacts only one reference or involves the coordination of changing more than one reference.
Okay, so then you have probably another wrapper around those that coordinates it.
Well, there are different kinds of references that have the different semantics.
Okay.
So now we could talk about the three main kinds.
Okay.
Atoms are the simplest. They're synchronous and they're atomic. They can only a unit of work can only involve one atom at a time.
Right. Mm-hmm.
Agents are like atoms. They're atomic. You can only impact one agent at a time, but they're asynchronous. So when you send an agent a function, that will happen at some point in the future. That call returns immediately.
Mm-hmm. Okay.
And the agent will process all the actions, they're called, that it's been sent in a thread pool sometime later. But it will ensure that they're performed serially. And finally, the most complex reference type is actually called a ref.
Mm-hmm.
And a ref can only be changed inside a transaction.
Ah, okay.
And refs are both synchronous and they're coordinated. So you can have a unit of work that involves more than one ref, which is what you would need, for instance, in order to take something out of one collection and put it into another collection.
So you would open a transaction and modify the two refs within it.
Correct.
Okay.
So this is a nice system in that you've moved everything into pure functions. So when you want, for instance, to test your function for adding something to a set, you don't have any state. You don't have to mock up anything, and you don't have to create a certain state in the world because that's a pure function. So testing your functions is all very simple. They don't involve the state. And then you have the separate problem of, okay, well, now I want to send that function into one of the reference types to be performed safely in a concurrent environment. So the two problems have been separated. And that you can make all these different semantics look exactly the same. They all look precisely the same. The state transition models are all identical. Pass a function to the reference.
Yeah. So that's why one buzzword that I hear around Clojure is that it has transactional memory. That's exactly this thing. The last kind of reference type, the refs are implemented using transactional memory, right? Okay. And I guess we've had an episode on this topic before. Also, I didn't look up the number, so you have to find that out for yourself. So,
although I would say that Clojure's approach to software transactional memory is very different.
Okay.
From what you might see in papers and in discussions about software transactional memory.
In which way?
A lot of people are working on software transactional memory with the objective of allowing you to take your existing code that manipulates objects mutably and just wrap that with transactions in order to eliminate needing to do locking. I personally am not fond of that approach. I don't think it's going to work. This approach I've mentioned with Clojures is very different. It emphasizes programming with values, right, and using pure functions. It emphasizes using values for aggregates, so the granularity is much coarser. And it uses multi-version concurrency control under the hood. So it's pretty different.
Yeah, and you also expose the fact that some data is mutable through transactions to the programmer. So you don't attempt any kind of transparency.
No, I think transparency is bad.
Yeah, I would probably agree. Yeah.
Right.
So
that's right.
So wouldn't I mean? Okay, I'm kind of putting words into your mouth now. Assuming that this reasonable support for time, values, identity, and concurrency has been one of the main drivers for building Clojure, wouldn't it have been possible or simpler to add this using some kind of library or framework to an existing language? In other words, why does this kind of stuff need language support as opposed to just a library?
In fact, it is a library.
Okay.
It's a library written in Java that you can use from Java.
Okay.
The whole thing about a language is, what a language is about. What does it make idiomatic and easy? So, for instance, you can use precisely the same reference types and the STM and the data structures of Clojure, all from Java.
Yeah, of course, but you'll die because you have to write all kinds of anonymous inner classes to represent the functions, right?
There's the function part, right? There's the lack of idiomatic library support.
Yeah.
For instance, with programming with values, you have to reassign them to something. So that's not idiomatic.
Right.
And so the lack of idioms and language support means using exactly the same constructs, the same underlying code from Java is extremely painful compared to Clojure, where it is the natural idiom.
Yeah.
And it's what you're doing by default. I mean, when you use Clojure and you use Clojure's data structures, you're programming this way always.
Yeah.
It's not something you superimpose later. And that's a good thing, because when you discover you need or desire, to add concurrency, you don't have to change everything in your program. You're already doing the right thing.
Yeah. Actually, I really liked your definition of what a language is because I struggle with that all the time since I work a lot with domain-specific languages and people always ask me what's the difference between a language and an API and why do I need the language? I can express everything with, insert X, whatever here. And this thing about making things idiomatic or making the right things simple to express, right? That's a very good definition.
Right.
Yeah.
So that's the key thing, and that's why all these independent pieces of Clojure, are designed together to make all the different parts, work well.
Mm-hmm. One last technical question before we probably talk about more community and adoption stuff. Another way of handling state in purely functional immutable languages are monads. I think we've talked about this concept before on SE Radio in Eric Meyer's episode, I think. Does this play a role in your Clojure language thing?
There are libraries for that. I think that monads don't fundamentally solve the identity problem.
Mm-hmm.
In other words, you can't use a monad for the set of logged in users in a long running program across multiple parts of your program.
Yeah.
All right. And that's why Haskell has an STM and mvars. It has those things because that's how you get multiple independent threads of control to coordinate. A monad is about one thread of control.
Right. Monad has nothing to do with concurrency. Yes.
Correct.
Mm-hmm.
And so you can't use the same construct for the two different jobs in Haskell. So I'm not sure that's always going to be the right construct then.
Mm-hmm. Okay.
Also, it's while there are libraries for Clojure, I think the concept is much more powerful in a language like Haskell where the type system is helping a lot.
Yeah, I mean, maybe that was my question. Is your type system aware of monads? And so the answer is no, and therefore it's not idiomatic to use them.
No. Of course, with macros, I mean, it can be made okay.
Yeah.
But the main thing that Haskell has going for it is that, because it can do inference on return types.
Yeah, exactly.
That's a particularly critical feature for monads.
Clojure is dynamically typed, right? So then there is you wouldn't be able to do the monad type inference thing anyway, right?
Well, Clojure does do local inferencing.
Okay.
For instance, in order to get calls to Java to work without reflection, we'd need to know the types.
Yeah.
But you'll find in Clojure you need to specify far fewer types than you would in Java, because once it knows a little bit, it's able to infer the result of this call is of this type, which means this next call is taking this type of arguments, et cetera, et cetera.
So then, is it duck typed or is it statically typed?
That's not binary choice.
Well, but if it's type inference done by the compiler, I wouldn't call that duck typing. I would just call that a compiled language or statically checked with type inference support. So,
well, the differences they come down to enforcement, right? So if I can figure out through inference what's happening, I can generate better code.
Yes.
If I can't, I'm not going to preclude it, which means that you'll get reflective code at runtime, which may discover that there's no method with that name.
Okay, but that means that I can specify type information in Clojure, and if it's present, I get statically compiled code as opposed to the reflection-based code.
Again, you have to be very precise. You will get code that's compiled with particular types and runs exactly identical to Java.
Yes.
On the other hand, you won't get code that precludes you passing different types.
Okay.
In other words, it's not a mechanism. It's a mechanism only for optimization.
Right. Okay, that's the point.
Not for precluding certain expressions.
Okay. But again,
it's not type checking. For instance.
But you can specify types, and then the compiler uses them to generate more efficient code, assuming they're correct.
Right. For the Java interop portion, that's correct.
Okay. Mm-hmm. Good. Is there anything technical about the language that I forgot to ask that you would like to mention?
Technical?
Yeah, like cool language features, technical as opposed to adoption community. Where can people find resources?
No. I mean, I think actually at the core of Clojure, technically, it's very, very, very simple.
Mm-hmm.
And in fact, that would be the biggest thing I'd want people to understand about it, is that it's it is extremely simple at its computational core. There are not a lot of rules. There are not a lot of syntactic things. There's and it's less even about syntax. It really computationally is extremely simple.
Mm-hmm. Okay, so then let's talk about the soft stuff. So, how is Clojure doing regarding adoption and in the general, let's say, language zoo that has developed on the JVM in the last 2 or 3 years?
I think it's doing remarkably well considering it's the most recent entry.
Mm-hmm.
The mailing list on Google Groups is now up to 3,300 members.
Wow. Mm-hmm.
So there's pretty significant adoption and utilization. People are now getting jobs in Clojure. It's being used by companies, and it started in startups, but it's definitely seeing some applications in other areas for analytics and various other things, financial companies. And
are there any typical usage scenarios? I mean, things for which the way Clojure works is especially, well, concurrency, I guess, but is especially well suited?
Well, I think one of the great things for me to have seen is that, it was designed to be a general purpose language, and it's seeing wide applications in vastly different domains.
Okay.
One area, if I were to try to pick something out that seems to me to be the first area that's kind of hot, would be like the Flightcaster use of Clojure, which they used it for machine learning, running on Hadoop on clusters, and their libraries have been integrated with some other statistical libraries for Clojure called Incantor. And it seems to be a hot area now where people doing analytics that would traditionally have used R and then had to hand their code to programmers to move into production could use Clojure to do that work, to work with large data from the get-go, and to be able to hand their models directly to people that, for use in production. So that's an area that seems to be booming, but it's also been used for web stuff and database stuff and messaging systems.
But it's probably fair to say that it can play out its benefits especially well if it's algorithmically non-trivial concurrent stuff.
There is that, although I think you might find that the concurrency part is used less often than you might imagine. I wouldn't say that that's its only trick. It's an extremely expressive language, and it does let you tap into the JVM's ecosystem. So there's a huge number of libraries available, and people are extremely productive with it, and that I think is what matters. A book is available, right, by Stuart Holloway? Yes.
So people can read that.
Yes, there are two more books on the way.
Okay.
And they can get early access versions from Manning. One is called Clojure in Action, and the other one is called The Joy of Clojure.
And are you writing one of those?
Nope.
No. Okay, I'm surprised. I would
I'm writing Clojure.
Okay, well...
Maybe at some point, but so far I'm too busy.
Okay, well, I guess that's a good sign. I mean, whatever. Okay.
So the community is great. The mailing list is large. We always have. Let me see. Right now we have 232 people on the IRC channel. Cool. These are other just kind of metric things. So it's easy to get help. Everybody's very friendly. It's easy to get started.
Good, cool, very nice. So I guess the only problem, quote, problem is to find a customer, at least in my case, who would want me to use Clojure instead of mainstream stuff, which is, I guess, at least in some environments, still a challenge, I guess, to convince the somewhat more conservative people.
Well, tell them you want to use this new Java library called Clojure.
Yes.
It comes in a jar like all the others.
Yeah. Good trick.
Yeah, no, I mean the adoption will play out at different rates in different industries, depending on the level of, conservatism and what people are doing. And but it has been interesting to see it used pretty widely already.
Is there tool support, IDE, syntax highlighting, and that kind of stuff?
Absolutely, it's actually really good. There's of course, there's Emacs support if you like Emacs. It's traditionally been a great place for Lisp. But if you like more traditional IDEs, there's very good support for NetBeans. It's a project called Clojure, which is it's great. It has completion for Clojure and Java. Very good integration with Java. Syntax highlighting, the REPL's built into the IDE.
Cool.
Similarly, IntelliJ has good Clojure support. Clojure is a recognized project type. It's it comes from the IntelliJ guys, and they've done a really good job. Somewhat newer and less developed, but up and coming is Eclipse support.
Okay.
So a bunch of options.
I guess if you have those three, then you're set.
yeah. And then of course Clojure participates in the general infrastructure for bytecode on the JVM. So debuggers and profilers for Java work with Clojure
on source code level.
Yeah.
Cool. Very good. Okay. I guess that's all I had prepared. Is there anything else you want to add, or?
No, I would just encourage people to try it out.
Yep.
And for sure, join the Google group and the IRC if you're trying it out. And there's plenty of help.
Cool, very good. So then, thank you very much for being on the show.
Thanks for having me.
Bye.
Bye.
Thanks for listening to Software Engineering Radio. Software Engineering Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig Reddit Delicious links and the /dot button. To contact the team, please send email to team@se-radio.net, or if it is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks to Charlie Crow and the Podsive Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.